Hello everyone, I'm Ruben He from USS Lab, Zhejiang University. The paper tries to understand and benchmark the commonality of adversarial examples. Intelligent voice devices are increasingly used in many critical scenarios, thus the security of speech content is an important topic. For the speech content, the adversarial example attack is the most typical attack. In such an attack, we generate a malicious perturbation, which is combined with the benign audio, and we can get an adversarial example that sounds like benign audio, but leads to incorrect recognition results. The perturbation and AE can be called adversarial audio. Attackers can use AEs to perform a malicious operation without being noticed. Recently, researchers have proposed various AE methods, and these methods have different optimization objectives, including different distance metrics and audible metrics. And we find it interesting that, despite the different methods leading to different AEs, these attacks result in similar success. The success consists of two parts. One is manipulating the speech content, and the other is not sounding like speech. So we have a question. Why do these diverse adversarial audio all succeed? To answer this question, we need to answer two sub-questions. The first one is, what is the similarity between adversarial audio and speech, since both of them can deliver the speech content? The second one, what is the differences between them that makes adversarial noise not sound like speech? In this paper, we plan to find the common properties of adversarial audio. This work can help us understanding how adversarial audio work and help us defend adversarial attacks. We design a measurement method to explore the distinctive properties of adversarial audio common to adversarial attacks. First of all, we determine the measurement object. We explore the existing adversarial audio recently. Besides the basic idea of generating adversarial example, there were many other works proposing various methods that can achieve additional goals beyond the primary goals. But we aim to analyze the most accurate noise that can only achieve the basic goal. Thus, we choose the white box noisy adding attacks as the research object. In the paper, we prepare three diverse and representative attacks and generate four types of audio for testing. Second, we design some physical meaningful features which can describe the property of audio comprehensively. We select 15 acoustic features describing the intensity, pitch, and other characteristics of audio. Based on them, we design 17 statistical features to describe the continuity, regularity, and the distribution trend of acoustic feature vectors. Finally, we obtain 255 acoustic statistical features as the feature set. Lastly, we ensure the properties are distinct from other audio and common to different attacks. We apply the significant difference test and the common sign check to design the commonality check method. Based on the above methods, we perform experiments to find the distinctive properties of adversarial audios, and finally we find the four types of properties. The first two properties answer why adversarial audio can change the speech content, and the last two answer why adversarial audio does not sound like human speech. The first one is filling energy gap. That is, the adversarial noise tends to manifest itself by filling in the energy gaps of the original audio. We can find it in the F-bank feature. As the figure shows, the areas with low energy in the original audio have overlaps with the energy peaks of the adversarial noise. ANs have this property maybe because, given an upper boundary of the noise intensity, the addition of noise to a low energy part can result in a more significant relative change, and it is more likely to change the decision of ASR models. The second one is speech-like morphology. It means the fragments of adversarial noise exhibit a similar morphology to human speech in the time-frequency domain. We take the temporal correlation as an example. From the left figure, we can find that benign audio and AN both have long temporal correlations, while the white noise have a short one. Human speech have prominent formants and long temporal correlation since it conveys speech content, and we guess advanced modules also utilize these features implicitly to recognize content, which cause AN have similar morphology to deliver content. The third one is disordered signal. It means the signal of adversarial example and adversarial noise don't follow the physiological rules of speech. The property have two meanings. One is that ANs and AEs are discontinuity, that is, they have significant changes within milliseconds on neighboring frequency points. From the left figure, we can find benign audio have short distance between peaks in the spectrogram, so it has a high continuity, and the AE is opposite. The second one is irregularity. That means AEs and ANs are in absence of harmonics and have unstable periods. From the left figure, we can find benign audio have stable periods in the spectrogram, while AEs don't have obvious periods. Human speech exhibits continuity and regularity since it is produced by humans' vocal tracts and vocal codes. ANs and AEs are free from these constraints and thus the perturbations are observed to be noise-like. The last one is abnormal linguistic pattern. That means the adversarial examples don't follow the linguistic rules of speech. From the recognition results of ASR models, we find AEs have long duration of phonemes and the long interval between characters. A possible reason is that ASR models don't consider the duration and interval of units when applying language models to correct the recognition result. Finally, based on these distinctive properties, we developed an AE detector. Our detector is effective for multi-attacks, including unknown attacks, such as black box attacks and game-based attacks. In summary, we investigate the distinctive properties of adversarial audio in terms of phonetics, which can help understanding how and why AEs work. Second, we discover four types of intrinsic properties of adversarial audio that can be best revealed by 12 acoustic statistical features. And the last one, with the discovered properties, we proposed an AE detector that can detect trained and untrained attacks. That's all my presentation. Thank you for listening.